Hey guys, it's Kate. As promised, this is proof 11.1, which we did not get to cover in the review session, but everyone really wanted to go over in maybe a more in-depth, slower treatment. So here it is. Just a disclaimer before we start, writing this much only is not acceptable for full credit on the final if this proof does appear. I'm going to be talking my way through this, so the main points that I make, the most important points I've put in blue on the board, I think the most important points. The different steps I've put in green on the board, but my justification at each step needs to be a part of the problem as you write it out on the exam. So, full credit question will illustrate that you understand every single step and you understand why you're doing every single step, and it's not just limited to what I've written here. So, we have proved that if X, which is a subset of Rn, is a k-dimensional manifold, and f is some function that maps from a set U to the real numbers R is a C1 continuously differentiable function, and there is some point C, which is an element of the intersection between the manifold X and the set U, is a local extremum of f restricted to the manifold. Then the tangent space of the manifold at the point C is a subset of the kernel of df. So df at the point C as well. So the very first thing that we want to do should seem very familiar to you guys. We're going to reorder C into active and passive components, our active and passive variables. So splitting those in half, we have our A passive and B active variables, and just as sort of a quick check, which is not part of this proof, but since you know that it's a k-dimensional manifold, that means it has k active variables. So from the implicit function theorem, we know that we can write these passive variables in terms of the active ones. So here we have our implicit function g of b, b being our active variables, and then we list our active variables underneath. So we have our passive variables defined by implicit functions and our active variables underneath. Here is the general case for how to write this, that x is a function of y, these being the passive variables, these being the active variables, just as a note to you all. Moving right along, we define a graph building function, g tilde of y, and g tilde of y gives us all of our passive variables in terms of our active variables, and then spits out our active variables underneath that. And this is the general definition of our graph building function. And then specifically at C, our graph defining function is going to be at B, because those are our active variables. And we have, so our passive variables here are defined by the implicit function g of b, and then also spits out b, our active variables underneath. So the important point to make here is that locally, the manifold is a graph of g of y. So it's a graph of the passive variables in terms of the active variables. That should make sense to you. Or the image of g tilde of y. And the image of g tilde of y is just spitting out all the passive variables in terms of the active variables and the active variables. In either case, it generates the manifold. And that's something that, by the definition of the manifold and construction there, that's pretty straightforward. So now we consider this function f, and to find the critical points of f composed of g tilde of y, well, first, people have been asking me, why am I doing f composed of g tilde of y? Well, the function f works on a point that consists of active and passive. So since g tilde gives me all the components of our point, that's why we're doing f composed of g tilde of y. And so to find the critical points of f, we would take the first derivative and set it equal to 0, right? It's a typical optimization problem. So we do df composed of g tilde of y. We use the chain rule here, which is equal to df composed of g tilde of y times d g tilde of y, and set that equal to 0. And so here's the important part. Parallel to the fact that the manifold is the graph of g of y, or the image of g tilde of y, we know that the tangent space of the manifold is the graph of d dg of y, sorry about that, that tilde was a mistake, or the image of dg tilde of y. And that's the really important part of this proof. At the point C, which we are told is a local extremum of f restricted to x, we know that since it's a local extremum, the partial derivative is equal to 0. So we plug all of these variables in at the specific example, the specific variables that they would be at the point C. So that turns, anytime you see g tilde of y, that's going to give you g tilde of b, since we're working at the point C. So that becomes df of g tilde of b times dg tilde of b, which, again, simplifying even further, gives me df of c, because g tilde of b just gives me c. Since here are active, and here are passive, and here are active variables, and that just equals c, times d g tilde of b equals 0. So what are we looking at here? Well, dg tilde of b here is returning a 0 when df of c acts on it. So that means that dg tilde of b is a subset of the kernel of df of c. And right here we said that the tangent space to the manifold is the graph of dg of y, or the image of dg tilde of y. Similarly, at the point C, the tangent space to the manifold at the point C is the graph of dg of b, or the image of dg tilde of b. So what we have here, dg tilde of b, is an element of the tangent space. It is the tangent space to the manifold at the point C. So by showing that when df of c acts on dg tilde of b, it returns a 0, we've shown that dg tilde of b is a subset of the kernel of df of c by the definition of the kernel. And by the definition of the tangent space, dg tilde of b is the tangent space to the manifold at the point C. So the tangent space to the manifold at the point C is a subset of the kernel of df of c. And we're done with the proof. If you have any questions, please shoot me an email, but that's 11.1.